Please go ahead.
Okay, dear all, we will start. I will start by welcoming you all for the ISPRS webinar. This is the second webinar organized by the Intercommission Working Group 2/1B on digital construction, reality capture, automated inspection, and integration to BIM. It is also to mention that these events are organized in the scope of the webinar series that are technical supported by ISPRS Student Consortium. And we will have two speakers today. We will change the order now since by organization issues. So we will start with Professor Borja García de Soto that I will invite it to join us and present his work and share his knowledge with us, please. Thank you very much for your presentation and to be available to perform it.
Well, thank you so much for the kind presentation and invitation to this webinar. It is a pleasure to be here. Thank you all for joining. I hope those in Spain, Portugal, and southern France were not too affected by the energy issue that has been going on yesterday. Hopefully everything is restored by now. So let me share. I hope you can all see my screen. And I would like to give you a kind of an overview of the work that is taking place in my lab, and mostly with regards to the way in which we go about the automation and robotization of some of the tasks regarding data acquisition. So I will not get into the details about the data processing and data management per se, but I would like to bring a new perspective about how we can go into this transformation of augmenting and giving additional tools to workers, individuals, surveyors, and so forth to facilitate this collection in a more automated manner. Before I do that, I would like to maybe give you a preview about where I'm coming from. I don't know if you're familiar with New York University. I'm an associate professor there, and we have what we believe is a truly global network university, meaning that we are globally strategically located. We have 3 degree campus around different continents, with the original one in New York. But we also, about 15 or so years ago, we have also presence in Abu Dhabi and in Shanghai. We also come with a number of different academic centers distributed across all continents, including different cities such as Accra, Berlin, Buenos Aires, Florence, New York, London, Madrid, and so forth. So we really give a true global experience, not only to the faculty, but also, and more importantly, to researchers and students being part of the NYU community. With regards to my lab, and just to put things in perspective, I want to give you a background about the backbone of the research that I do. We look at the automation and robotization from different angles. First of all, we want to ensure that it's sustainable, right? In not only the traditional way of sustainability, meaning the environmental perspective, but also we want to look at the other layers of sustainability. Probably as you might think of, the financial perspective, make sure it's feasible from the financial point of view, but also from the social implications. And we are seeing a lot of kind of drawbacks or some kind of resistance when they try to automate and robotize different tasks, because one of the big questions is what's going to happen with the current roles and the current people. So we want to bring this dimension into perspective. The other part, and probably similar to many of the work that you might be doing, has to do with modularization, pre-construction, trying to look about these settings in which we can control the construction processes, we can control the assemblies, and this is what many of the maybe work that you have been working on regarding computer vision application, analysis of point cloud data, and all these things could make some impact. At the same time, and based on the things that I was just mentioning, all this data that is being collected through the application of new technologies now empowers us to really exploit that through the use of artificial intelligence. And I'm sure all of you have experience with that or have been working on development of AI techniques to enhance and really take advantage of this technology. The other component that I focus on has to do with the robotics side. And robotics in the pure sense of how we can integrate robotic systems at different levels of automation to help us through different processes. It could be during the actual construction phase, which still is in a very preliminary stages and very many challenges that we have to deal with, particularly because we need to address how we go about building, how we go about monitoring construction processes, how we go about monitoring progress itself. We need to change a little bit the mindset and the status quo, if you will, to ensure that we are more aligned with other manufacturing sectors that, decompose processes in a more organized way instead of having these kind of chaotic environments that are very hard to robotize given the current systems that we're dealing with. And last but not least, we're looking at the integration of technology in all the different senses. And technology, in the way that I look at it, has this broad sense with regards to any method, any system, or any devices that really result in scientific knowledge and scientific improvements. And to kind of close this section, I would like to ensure that we are also, by adding all this technology from the artificial intelligence part, from the modularization components, from robotics, integration of technology, and so forth, which are bringing great things to construction, we're also opening vulnerabilities from the cyber perspective. So we want to ensure that we consider also cybersecurity considerations and all the different layers across the spectrum of this research. So now getting a bit more into the specifics and motivation of how we could automate and robotize data collection, right? Particularly in construction projects. And all of you have heard about this argument, maybe from different perspectives about productivity. We have not drastically changed the way we go about building and the way we go about monitoring in the sense of the human component, right? Of course, there has been a huge change in the technologies that we are using and the process of the data that we collect. But in the fundamental aspects, there has not been a lot of change. For example, in this image, you can see the way we go about erecting steel frame structures, despite the advantages that we have seen in materials, in maybe the operations from cranes and stuff like that, we still heavily rely on a very labor-intense workforce. There has been a lot of changes with regards, obviously, on safety. That's probably the most obvious difference in these pictures. But over the last 90+ years, we still have a lot of opportunities to, improve things, and in the context of how we go about collecting data and how we go about the processing and systematically a way of collecting that data. We're also seeing other factors that are kind of accelerating these changes, right? And I guess you're all familiar with what's happening, particularly in Europe and developed places where the workforce is declining quickly. We are running out of workers. And to be realistic, construction is not that appealing anymore. We are kind of falling behind other sectors, and younger generations are not that interested in going to construction sites. They're really very hard work environments, tedious, dangerous. So we're seeing a decline in population, but also a decline in interest. There is now this concept about how we can go and modernize civil engineering, construction management, and so forth. Technology is playing a significant part, but still we need to be conscious about what are the implications in the long term and how we can compensate for that potential gap. We're also seeing, as in many other industries, like labor cost is skyrocketing. And at the same time, like in most technologies, the price of technology goes down, and particularly the price of robots. So in the old days, I mean, we look back maybe, I don't know, in the 70s, 80s, Japan was one of the pioneers of robotized construction sites. The main challenge they had was timing, right? It was very expensive the technology was still not quite fully developed to robotize, despite the efforts that they had made in this regard. So now we are in kind of this perfect storm, or this ecosystem, that we have high labor costs, low robot prices. So now we start thinking, particularly on the construction company side, does it make sense to start looking at ways to robotize my workforce for things that could be relatively straightforward to do, like data collection, doing progress monitoring, for instance. And that is actually kind of the main axis of research that I work on. And we're trying to really put this in practice in real construction sites. So we have a fleet of different robots, and I would like to focus on this particular element. I would like to see how we could use these systems as an additional member of a team, if you will, that would allow me to, add whatever payload would be required. It could be a laser scanner, it could be cameras, it could be microphones, whatever type of data you need to collect, that would allow you to systematically go through your sites, collect the data, gather that data in a way that could be further processed and then utilized for whatever needs. And this is not meant to replace humans. It's a way to augment humans and make them more efficient, more productive of things that they can really provide in value at. So here you can see a couple of examples. And in the place that I'm located right now in Abu Dhabi, we have many construction projects going on. We're lucky to have connection with industry that allow us to use their projects as a test bed. So we move away from the lab and deploy these things, and this is where you really realize the challenges and the opportunities that you have to integrate these systems with different sensors, with different capabilities, to really be a valuable member of a crew in a construction site. So I believe we're gonna hold the questions until the end, correct? But okay. So let's hold the questions until the end, but feel free to make any comments if you will. That's fine. So let's go about a little bit about the thinking process of how you will go about designing the correct platform that would allow you to gather the information that you need based on the limited knowledge and the limited skills that you might have from the construction perspective, meaning that we're not robotists, we're not computer scientists, and so forth. So we need to have a clear roadmap that will still allow us to go systematically through a process that will help us to choose the right platform for our construction applications. And here you can see, I will not get too much into the details, but a generic kind of process that, depending on the type of frame that you will be using, meaning this is going to be an open source or proprietary platform with the pros and cons of each, depending on the application, is it going to be happening indoors and outdoors? Of course, there are many things that you need to consider regarding localization and navigation perspectives when you're dealing with indoors, and you have some limitations with regards to the type of sensors and the type of components that you can use. For example, GPS is becoming now an issue, so you might have to move away from that and move towards SLAM techniques, more traditional approaches for navigation. Locomotion, how is this going to be happening? Is it going to be a wheeled or a leg robot? Is it going to be a drone that is going to be flying around? What are the safety concerns? What are the elements that you need to look with the jurisdictions where your project is located? What about the type of interaction with the robot? Beyond the human-machine collaboration, let's say, is this going to be something completely autonomous? Or are you going to have this teleoperated system that you still have the humans in the loop and controlling the process about the data that you're collecting, the location that the robot is being placed, and so forth? And you can see a little bit of all the main steps, but ideally, once you go through this process, you will be able to come out with a platform that will ensure that it's able to fulfill the requirements that you need with regards to the data collection perspective. What is important to know here is that we don't have to start from scratch, right? We need to look at what tools are already available. And there are many opportunities now in the market that allow us to have enough flexibility that we don't have to start from building, let's say, the robotic platform from scratch. We can just have the basis from it and start in a modular perspective, add payloads to it with regards to the specific use that we want to use. What is important as well is to have a good understanding, and in this slide I'm trying to show the kind of sort of complexity that is involved across the different levels of communication strategies that you might want to consider for your platforms. So for example, here, starting with the bottom layer, we have the hardware component. We talked briefly about that. What type of platform you're going to be using? Is this going to be indoors or outdoors? Meaning it's going to be a terrestrial robot versus aerial robot. Is it going to be leg versus wheel? What are the limitations with regards to the state of the actual implementation? What type of sensors are going to be used? Is it going to be a 3D laser scanner that is going to be continuously registering the environment as you're moving, or you need to predefine waypoints for the robot to go and collect data? What about the IT network? How is this going to be connected with the overall network of the organization, with the network on site? We know limitations on construction site at the beginning with regards to connectivity, depending on location, depending on the status of construction and so forth. Then you need to integrate all that with the actual brains, if you will, of the robotic platform. Typically, we're using ROS, Robot Operating Systems, that allows you to integrate different elements from the actual payload that is added to your robot, in this case, a 3D laser scanner, but it also includes all the sensors that are built into the robot for navigation and so forth. Last but not least, you need to understand what is the control mechanisms. Is this going to be, as I mentioned previously, fully automated? We're very kind of far behind in this kind of approach, particularly given the, unstructured environments that we're dealing with, particularly in the early phases of construction. Once you start moving into final handover of facilities and operations phase, let's say, then things might become a bit more easy and straightforward, but still a lot of challenges with regards to full autonomy. And last but not least, you have to deal with about the visualization of the data. How is that data going to be shared? How is it going to be stored? How is it going to be pre-processed and post-processed depending on the applications? And this is maybe where most of your work is going to be dealing with, right? How once this is the output of this, process, how this could be optimized for further utilization in your developments. So let me just give you a quick example of some of the prototypes that we're dealing with, right? With regards to the payload, we need to deal with both the navigation components. So we need to ensure that we have the ability of the proper mechanisms that allow us to understand the environment where the robot has to go through, but also that we have the ability to add whatever systems or whatever equipment that we can capture data that can be further processed. Here on the left side, let me just use the pointer, maybe it will be easier. Yeah, so basically we have the navigation component. So we have a LiDAR that allow us to use and employ traditional SLAM mechanisms or SLAM techniques for navigation and localization purposes. We have a very modular and workable structure or framework that allow us to change things quickly, right? We want to have the ability to have a modular approach and add and remove payload. And by payload, I mean the sensors that are required for our particular application. And of course, in this particular case, we'll be using a 3D scanner, but this could be like a static one in the sense that you might have to stop and then collect the data, or you could have more dynamic ones, like this hover map, that allows you to continuously monitor and capture data and register data. Of course, there is a trade-off with the noise that you might have to deal with later on. But the point of this is to allow you to understand that you have a lot of flexibility to modify and change your platform to kind of complement whatever needs that you need, in the sense of the same that you would do if you have an operator, or you have a human collecting the data in a similar fashion. So this example, we show you the difference about the different payloads that you could use. So here will be more on the 3D laser scanner. Here you can also add infrared cameras, again, whatever requirements you're dealing with. With regards to mobility, this is a big challenge. Or maybe of you might be questioning, okay, but how is this gonna, navigate through a, kind of chaotic construction site where you have workers around, you have scaffolding, you have temporary structures, you have temporary storage areas. So it's not trivial to have these systems moving. Of course, the more fundamental is the limitations that it has with regards to mobility. And that's when we start to think, okay, are we looking at a wheel platform? or we look at a leg platform, right? You can see the advantages and disadvantages of each of them. Here on the left, the holonomic platforms allow you to, have very narrow spaces navigated. You can, the rotation perspective is relatively phenomenal, but you cannot climb stairs, for instance, or you might not be able to interact with the environment, like in the case of the image on the right, where you have a robotic arm that you can move things around if needed. So you can think of these platforms as additional workers, as I mentioned before, and each of them with their skill sets and their abilities, right? And in this context, you can start thinking of multi-agents, like how you can have the same way you go about defining your crews, defining the type of task that you're going to be doing, and then selecting the team members for data collection, surveying, monitoring, whatever it is. And you can put it in the perspective of, okay, let's call them agents, and let's try to see how we can integrate and create these systems, right? So you have these multi-agent systems that, for example, in the sense of applications for inspections or project monitoring, you can customize and define the different agents depending on the payloads that you're interested in. For example, agent 1 will be able to collect data through a laser scanner, for instance. Agent 2 will be able to, interact with the environment as needed, remove obstacles, and facilitate the performance or the mission of the other agents. And of course, another agent could be us, could be humans, right? We are not gonna be completely replaced yet. We need to be in the loop to ensure that whatever these other agents are doing, similar to a manager perspective, that we are providing, the final decision about the process. And all this needs to be integrated and properly communicated. And this is also when the human-computer, human-machine interaction starts to become important. Not only understanding the capabilities and the skills of the different agents, but also the payloads and the different equipment and sensors that the different agents are dealing with regards to the particular applications. Let me show you very briefly an overview of how this would look like, right? And we are doing currently experiments to investigate the use of exploration algorithms and exploration in the context of how we can go about navigating environments without a lot of prior knowledge, and how we can use this in this multi-agent, kind of configuration that each agent will have a specific mission to accomplish. So starting with the different agent perspective, right? You will have, as I mentioned before, identified what is the scope, what are the things you want to be collecting, what type of data you need to gather, and then what are the skill sets or the characteristics of these agents. And it could be a human, it could be a robot, it could be a computer, whatever it is. Then you need to define the different capabilities and specifications, right? And this is basically going to the beginning about how you go about designing these platforms, thinking about how you will go about designing or finding the right crew composition for your project. And last but not least, you need to ensure that you have, like you will do anyways, the right equipment and the right hardware that will be necessary. And this could be expanded, right? And a number of agents that would be required. With regards to the exploration, as I mentioned briefly before, we just want to ensure that you have the ability to navigate spaces without a lot of prior knowledge. You might only need information about what is the area that you need to cover, or what are the characteristics of the space that you're dealing with, and what type of information would be critical to collect during that particular mission. And this mission will include the exploration algorithms that will deal with the navigation and ensuring that the robots are able to localize and go around their missions in a coordinated way. But also you can start thinking about the task-specific applications. So for example, Agent 1 is responsible to map the environment, and then through whatever payload that is applied, collect data that can be later processed and used, kind of substitute and enhance what the humans will be doing, but in a more systematic and thorough way, and also in a higher frequency, right? You could now start thinking, I could do the collection of my data every 2 days, right? Or every 3 days or whatever. So frequency will be important. And then this will allow you to, bring all the pieces together and get you what you need at the end of the day. So an example in practice, right? How this will work in the lab. we have tested this technology. And here you can see on the left side, we have exploration map. Basically, the image on the lower side will show you the points that the robot can still navigate to. They have not been fully explored, so you have still ability to do that. And here you have a cost map, an obstacle map that is generated from the LiDAR on the robot. At some point, this robot, the mission of this robot was to map and 3D or digitize the whole environment here, but there's an area that cannot access. So without any human intervention, you could have another robot that would allow you to, understand what are the issues that this robot is having, not accessing this space, have humans to confirm what action needs to be taken, and then go ahead, assist the robot, remove the obstacle, so this robot can communicate, provide a complete information, remap the environment, and come out with the final goal, which would be 3D representation using a laser scan. And I will show you a quick video of how this was done. This is in a controlled environment. We have a paper published on this, so if you're more interested, you're welcome to take a look at it. And I will quickly run this video, see if it works. Okay, so here you can see the robot. This is this agent is specifically designed to get the point cloud data. At some point, it reached all the spaces that were able to be reached. However, it was not a completed mission yet because the complete area was not finished. What happened there was that it communicated with the other robot that had the ability to interact with the environment. And that robot was sent to the location where the obstacle was placed. A human remotely, it could be in the same place or it could be in a different location depending on connectivity, was able to confirm and provide commands to the robot with the robotic arm to actually interact with the environment, move the obstacle, provide information to the other robot to complete the mission, and then the other robot go back and remap the environment and complete the task that was assigned to it. And the final product would be to get the point cloud in a semi-autonomous way, in the sense that you might have still some interaction from humans, but the navigation and communication will be mostly achieved autonomously by these systems. This point cloud then can be further used, analyzed for whatever purposes, comparison to a plan, a beam, or whatever things that you might think of. As I mentioned before, we're lucky here to use real construction projects to test our systems. And this is one of the most important parts for us. And I'm happy to see interest in general for industry. In particular, I'd like to mention ALEC Construction. They are one of the big developers in the region. They have many projects in Dubai and in Abu Dhabi, and they're also expanding to other places in Saudi and North Africa. But the ability to really go out of the lab into a real site is when you really get excitement about, okay, what are the challenges that I'm gonna face today? What are the issues that I didn't think that I need to consider? And it goes from very silly things like, okay, maybe the configuration of the scaffolding that changes from project to project is actually messing up with the recognition algorithms for the navigation component. And also the navigation might be facilitated with April tags, some kind of markers that you have on your site, but this is probably not practical because of the changing nature of your projects during the early phases. Of course, going up and down stairs, going around obstacles, going around extreme weather conditions. Here it gets particularly hot in the summer, which affects the readings from the sensor, the battery life, all these things you can start thinking about outside of the lab. And some of the basic applications, again, trying to translate this information and this technology to construction is not trivial, right? We need to first show them the value, convince that this has potential to improve frequency, improve accuracy, improve or remove bias from human operators. And at the end of the day, you're able to gather data that you will get anyways, but ultimately, in the long term, keeping economies of scale into account in a more cost-effective and efficient manner. And other things that we need to do is how we can fully automate the processes, right? So it's not about the navigation part, which is a problem that for the most part has been typically addressed. We need to deal with specifically with construction settings, which are not trivial, but also how we can integrate the payload, the sensors that we want to use. So we try to remove as much as possible humans and put those humans where they really add value in the data processing, the data analysis, the data management, if you will. So this we can do through the integration of how we can say, for example, the BLK 360 integration with ROS. So we know once the robot has achieved a specific location, it will trigger a command to take, scan, and move on to the next step, and so forth. So we go through the ROS network integration. We save and integrate commands and nodes through API provided by the manufacturers. We then provide those commands to initiate the scan. The scan can be configured based on the characteristics of the equipment with regards to the density, the type of information that you need. This is going to be just, RGB data, thermal data, whatever is needed. And then how that data flows back into your network and ultimately stored in a safe way that you can further analyze and use for whatever applications that you're dealing with, right? And you're all familiar with the types of things that you might get. And as I mentioned before, this is just an example. So you need to think about, what are the main steps that you go, and this is very common, nothing new here. It's about the data collection, data transmission, keeping in mind security, right? We want to ensure that the data is securely transferred, that there is no opportunity for tampering the data, but this would be true for any application. And then how you can visualize this data in real or near real time. This is important, and we found this to be important because we wanted to ensure that once we deploy these autonomous systems or semi-autonomous systems, that they are collecting all the data that you need in an efficient way. And if not, you will get red flags about maybe this area was not covered enough. You might have to send another surveyor or another robot to that particular location, or the quality of the information here was not sufficient. So you want to have this kind of dashboard that allows you to have a better understanding about the real-time visualization of data that you're collecting. And of course, data storage and further processing. So probably, I'm not sure if I'm going too fast or covering too much, but I want to now get to some specific applications. I would like to maybe just show you an example of how we're trying to use this for the quality control in formwork systems, right? Again, it's all about how traditionally this will be done in this region. At least you will have this formwork system with very detailed drawings about the shop and installation processes. And then you typically have an inspector that will be checking and ensuring that the studs or the different components have been properly installed before they add or place concrete to ensure that it will not fail, or it will be provided the necessary integrity during the curing process. So we were comparing these with how we could use now these autonomous or semi-autonomous systems with the proper payload. So here you can see a 3D laser scanner that will allow us to scan the place, and that will allow us to later on process this data through different techniques. And this is really beyond the scope of this presentation, but I would like to show you a little bit of the outcome of that. You will get the robot on site, take the scan, and then the scan can be further processed by different methods. This is just one example that would allow us to, identify different members, classify them, provide proper identification, and then conduct the measurement that can be compared to the measurement that would be done traditionally using a measuring tape, and gauge and assess the performance and the value. And of course, we need to add the dimension of the timing, how long it took to set up the system, how long it took to take the scan, how long it takes the human to do the same task, and then do a cost comparison, but also look at the social perspective. What does it mean for the inspector? What is the inspector gonna do if the robot is gonna be doing this, and so forth. Another application was on safety cases. We wanted to use this system. We didn't employ here the point cloud data. We instead, I don't know if you can see here at the front of the robot, we have a 360 camera that was able to collect data and images in a regular basis. We have a base condition about the type of barriers that you might expect, like a full bore barrier in a staircase setting, let's say. This is simulating basically an opening in a construction site that we want to protect for falling the workers, and then different possible configurations of improperly installed barriers, right? And then we can use this data collected from the robot in a real time through models that have been developed using computer vision to identify dangerous or improper installation of these barriers, for example. So again, just to put a little bit into perspective, how starting from the definition and design of your platforms, what type of payloads you can use, how you can integrate multiple agents to collect data and augment what humans, inspectors and human surveyors might be doing, and then how you could further process this data into practical cases. I mean, you have many, many opportunities and many, still also many challenges, right? And I want to also make an emphasis on how we can make this really accessible technology for construction. And this is one of the main challenges that we're seeing. When we go to a contractor and say, okay, we can robotize some of your tasks and you can really get some benefit. And they say, well, that sounds great, but look at my crew. They have no clue about robots. How are we gonna be dealing with robots now? We have to deal with all these things that you're talking about, RAWs and all this coding. So this is not gonna work. So how can we, close the gap and ensure that non-skilled personnel can have this interaction with robots in a way that facilitates and enhances, the performance of the projects overall? So I guess probably, I don't know if something is coming to mind, but if you have seen lately the developments of large language models, right? And in particular, multimodal large language models that allow us to really process data, images, text, voice, and this is really a game changer in the human-machine interaction and collaboration. And we have now moving into this direction because we believe is the next step into what will make these technologies fully integrated in construction operations, with many of the limitations with regards to the real settings that we need to deal with. But this is a very, very good opportunity. And we have been experimenting with some cases in which we allow, common conversations, right, between humans and robots. So you can just communicate using multimodal large language models. For example, you're a construction worker, you need help. You will have the ability to interact with that, robotics platform, robotics system that is able to gather your information, process this information in different steps. Right now, we are relying mostly on cloud-based applications. This is not ideal because of the latency and because many places you don't have this connectivity that you need. But also, we have constraints when we try to move these systems into the local networks, in the local systems itself, right? Like the platform that we're dealing with, because the models are big. However, with the new reduced models, we're able to have these embedded models in the systems that we can deploy and avoid this kind of interaction with the cloud. But you have the full process, right? You go from the text to speech through the large language models. You have through the text to voice. And then the robot eventually being able to process that and communicate back to you and have this more informal, let's say, communication without the required skill sets that will be needed in the background. So this is a high-level view of how this interaction would look like, right? So you have, the ability to speak to the robot. Then you have the different multimodal levels that I was mentioning before about the speech, text, and vision, and then how you close the loop and provide this interaction in a kind of intuitive way that allows, construction workers to interact with robots. And we are working on this project that we call PACA. It's a personal autonomous construction assistant. We have a different number of sensors and payloads installed in this particular case. This is mostly meant to provide support and to provide tools to construction workers. On one side, we have to equip the workers with the right ways to communicate. And in the context of construction settings, right, they are very noisy environments, typically, and structure. So we have this kind of on-demand kind of communication, right? So you have the ability to interact when needed. Also makes sense. So the robot is not collecting, information all the time. But once you engage with the robot, you have full attention and allows you to interact in a one-to-one basis. Also, many of these models are multi-language, right? So you could be in this region, it's very common that you have people from different places, different languages spoken on the site, and communication is an issue. This multi-language application allows you to, no matter what language you speak, the robot is going to be able to understand you and reply back to you in the same language. With regards to the robot application in this case, we have different payload that is being customized. We have a Jetson RNNX for the development and deployment of the systems on the robot, so we don't have to have this cloud component that is causing to be an issue with regards to latency, but also we found many places that we could not use it because we didn't have a connection, a reliable connection. Then whatever payload, as I mentioned before, in this case, we're using 360 cameras that we're using to collect data for progress monitoring. And this could be later imported into different packages or different platforms. Then we have the ability to, interact with the user. So we have a microphone, we have a speaker, and also we have a camera. So the robot could be taking images in addition to the 360 camera for localization, but also to understanding some of the cases of the interaction with the humans. For time constraints, I will not show the video here, but if you have a chance to scan through this QR code, it will take you to a video that shows a demo of how this experiment is taking place in the lab. And I would like to conclude with this. Of course, all the items that I have presented here are not happening only by me. I have a great team behind, and the ones really doing the hard work and all the advancements of the points that I have made here. In addition to the robotic platforms, we have the human component of the lab. And with this, I would like to conclude my presentation. Thank you very much for your attention. I'll be happy to address any questions now or later. Thank you very much.
Thank you very much, Borja, for this excellent presentation. Very stimulating, very clear. I think, in fact, I invite all to put questions also in Q&A, and then we can in the end make some chat and a conversation regarding all the questions and see all the main topics of that the attendees want to discuss. And right now, I think we will pass for the presentation of Martin Garcia. He's an industrial engineer specializing in geometrics and digital construction technology. And we will play a recording presentation, but then Martin is also joined us for the Q&A and to the global discussion about all the topics here presented. Thank you.
Good morning, everyone, and welcome to this webinar named Progress Monitoring of Construction Sites Using. Good morning, everyone, and welcome to this. Good morning, everyone, and welcome to.
Was it audible when I was sharing the screen?
Yeah, yet with the audio is fine.
Okay, thank you. I just wanted to make sure. Sorry, I'm sharing it now.
Okay, thank you, Lakshmi.
This webinar named Progress Monitoring of Construction Sites Using LiDAR and Computer Vision. My name is Professor Dr. Maarten Bassier, and I'm a member of the KU Leuven Geomatics Group that specializes in Scan to BIM and Scan versus BIM processes. The topic of this webinar is very clear, but before we start, let's get into the main problems of construction sites. So first, something about the construction industry. The construction industry is very important in every country, making up of around 10% of the GDP. However, this industry is at a risk, growing only 1% per year in the last 2 decades, and profit margins are at an all-time low. Innovation is needed at every level, from design to prefabrication, construction, and even as-built production to remedy some of the key obstacles. Our research in LiDAR and computer vision techniques can significantly lower the failure costs that can ramp up to 20% of the project total budget. Crucially, the key is combining these optical techniques with digital twinning to create a reliable spatio-temporal blueprint of the construction site that allows progress monitoring, quality control, and even quantity takeoffs. Now, because construction monitoring is so closely tied to digital twinning, it is crucial to understand that construction monitoring affects all three stages of construction. Specifically, we need the innovations from construction industrialization, digitization, and finally, the monitoring itself. Let's take a look at each of these aspects. If all three conditions are met, we will facilitate the tolerance control and specifically the stakeout on site. This is currently done with the use of total stations, but this can be made more repetitive if we have prefabricated, standardized, and automated procedure in place on the construction site. Now, the second aspect is construction digitalization. This digital twinning through the use of building information modeling and its exchange format IFC. I already mentioned the database of tens of thousands of elements that we need to use with accurate texture and geometries instead of our conventional PDF plans. Now, aside from this BIM database, we also need to extract information from the building process. This BIM process, for instance, in the form of lean methodologies, have detailed plannings that we can use to lower the computational complexity of identifying and matching observations with certain objects. Very concretely, we don't want to identify and evaluate observations with the entire database, but focus specifically on the relevant objects that are being constructed at a certain stage. Now, before we commence construction, these optical techniques can already contribute in the form of as-is measurements of the site as a whole in order to compute clash detections and avoid costly failure costs compared to the original design. The third and final aspect is the key topic of this talk, namely the construction monitoring itself. The capture of optical data on your site, either in the form of imagery or LiDAR information from aerial or terrestrial vantage points, and the calculation of certain parameters from those observations. Specifically, we will discuss the extraction of quality control information or tolerances, progress estimation, which can be binary or more complex, in which that report the state of the construction, the site planning, quantity takeoffs, and finally safety inspection, which is a little bit more of a niche, but there are opportunities with remote sensing or optical data to automate these tasks. Now, how do we facilitate these tasks using the optical data, specifically using close-range observations? Here we see an overview of some of the tools that are currently being deployed on site that go all the way from handheld cameras and LiDAR scanners to full robotic applications, for instance, the Spot robot, which can be mounted with terrestrial laser scanners in order to capture very highly accurate information of the construction site. Overall, there are three parameters to consider. First of all is the coverage of the site, namely how many pixels or points are used to cover certain objects. That specifically can be translated to the percentage of coverage compared to the theoretical design of objects. The second aspect is the accuracy of the observations. Specifically, laser scanning will be more accurate than photogrammetry, but might have a lower coverage. And then finally is the timeliness of these observations. Nowadays, we're seeing plenty of opportunities for drone-in-a-box solutions where we have daily flights of construction sites using UAVs, but also tower crane cameras can provide very timely measurements of ongoing operations. Instead LiDAR typically is less frequent, but then, of course, is much more accurate. Now, before we go into the actual tasks, let's consider some of the data sets that are being used, namely these BIM models and these observations on site. Specifically, KU Leuven has a collaboration with the ITC U20 University for the use of data. We have tracked throughout many epochs 2 construction sites, one by each university, that will be used to create an open source benchmark where researchers and industry professionals can develop methodologies on these construction sites and actually progress the industry forward as a whole. The first data set is the ITC construction in the north of the Netherlands in U20, captured by the Geomatics group over there. It consists of close to 60,000 elements covering the structure, MEP, and architectural finish of that building. It was captured in 4 measurement epochs, and it has about 4:1 ratio in primary compared to secondary elements. If we take a look at the overview of the ITC recordings, we actually captured UAV structure for motion data, indoor mobile mapping system data, or IMMS, terrestrial laser scanning, or TLS data, and finally also some low-cost sensory data with an iPhone and a depth sensor to compare to the high-end sensors. Now, if we take a look at the data coming from these 4 epochs, we see big differences between the different capturing methodologies and systems. For instance, the structure from motion pipeline quickly generated over tens of thousands of elements in only 4 epochs. However, this is absolutely dwarfed by the LiDAR data, which is about 450 million points with the IMMS and 3 times as much, having 1,500 million points with the TLS data. This building in the structure phase could be captured by about 150 scans, which is about 3 days worth of scanning, indicating that the timeliness of LiDAR data and also the cost to perform these measurements is quite high. Now, the low-cost sensory data is obviously only 5 million points, but this was only a limited test case and cannot be used for the full structure. The second data set is captured by KU Leuven in the city of Ghent. It only contains the basement of an apartment complex and is limited to elements in the structure phase, which has about 2,600 elements. However, it was captured over 17 epochs, ranging all the way from the foundations to the finishing of the basement and starting with the upper construction of the apartment buildings. If we take a look at the data there, we again see that we used TLS data to capture the sites typically once every month, and we paired this with UAV recordings and handheld imagery using a DSLR camera to perform photogrammetry aligned with the laser scanning during these 17 epochs. Now, if we take a look at the data, we again see a massive number of TLS points, namely over 2,000 million points or 200 scans with an average of 20 scans per construction epoch. This means that we didn't capture the full construction site, which is economically unfeasible, but only captured the parts where it was being worked and relied on the static environments, namely the areas where they didn't work, to co-register the data to previous epochs in order to efficiently capture the full site. For the structure from motion, we again see about 2,000 images per flight, or 17 flights, which is also paired with the handheld structure from motion, which had a total of 11,000 images over these 17 epochs. Now, how do we spark innovation for the previously mentioned tasks, namely the quality control, progress estimation, site planning, quantity takeoffs, and safety inspection? Now, specifically, we need to take a look at the key obstacles behind these tasks in order to allow them to be automated more successfully. Specifically, we will be hosting 6 open source benchmark competitions that focus on the alignment accuracy of the information, the reconstruction or the depth estimation from photogrammetry and LiDAR, the progress estimation and quality control itself, because we feel that this can be directly computed from those data, And then finally, a semantic segmentation and object detection on site, which lay at the basis of many of these tasks. Let's take a look at the alignment accuracy. In fact, we can see in our data sets and in the industry as a whole that a number of images cannot be co-registered correctly in the coordinate system. And if they are not co-registered, they cannot be used for the downstream tasks, such as progress monitoring. In fact, only 65% of our imagery in these datasets are registered correctly, with handheld and low-cost sensory being the most impacted. In fact, of the remaining imagery, which account for 37,000 images, we are still looking for methodologies to more reliably align these datasets. Now, this might come as a surprise, but there are in fact significant alignment obstacles for structure from motion on construction site. We see them listed here, with the lack of features being the first major obstacle due to watery reflections and self-similarities on construction sites, specifically during the structure phase. Second, we have exposure issues between the inside and outside of buildings. Specifically, the transition from an open to an indoor area can be detrimental for co-registration procedures. Reflections is a major issue, both in TLS and structure for motion pipelines, as is narrow passages, repetitivity, and the construction changes itself. Currently, there are no commercial packages, for instance, like reality capture or Metashape, that can deal with these issues. More methodologies are needed, for instance, through Colmap deep learning features, in order to more reliably geolocate imagery on construction sites. The second task focuses on the reconstruction accuracy, because we still see that both TLS and structure for motion pipelines struggle with reconstructing certain aspects on construction site. Specifically, structure for motion pipelines struggle, as you can see here with this rebar field of a to-be poured concrete slab on a construction site. You see clearly holes in the reconstructed rebar field, which indicate that the depth estimation is not reliable. Furthermore, we see a 1 to 3 centimeter difference between TLS and structure for motion reconstructions, which can hamper tolerance control or tolerance estimations for certain elements. Remaining obstacles include mixed edge pixels, or the deflection of a part of the laser beam or pixel, confusion of pixels near the side of objects, leading to a erroneous depth estimation. This is a source of noise which can easily be confused while performing tolerance control of objects. It is specifically prevalent near corners or small ledges. A second obstacle are reflections, mostly due to water. Both TLS and structure for motion pipelines struggle with this environment because it leads to ghosting data, or data that isn't there but still resembles the structure of the building surrounding it. This can lead to misleading results in terms of progress or quality estimations, as it might indicate false positives. The same can be said for absorptive materials that leave holes in the data, which can be seen as occlusions or objects that cannot be seen or can be misinterpreted as not being built. Now, depth reconstruction is an extremely challenging task, which is the topic of ongoing research. In fact, this is not limited to construction site, but is an overall challenge in the community. And one of the key data sets that is being used to advance depth estimation is the Matterport 3D challenge, which provides over 200,000 RGBD images to advance single-shot depth estimation or structure for motion depth estimation as a whole. So the next task is progress estimation. In this task, we try to determine whether an object is built or not. Now, typically, this is a binary query where we only have two states, namely built or not built. However, we feel that this can be more nuanced, Namely, on the construction site, it's often very relevant that we also identify the intermediate stages, such as being under construction, and of course, we also need an occluded state, which is unobserved. Based on these states in the consecutive epochs, we can actually periodically assess the progression of each of these elements. Now, current state-of-the-art methods focus on the presence of points or pixels in the vicinity of an object. Now, unfortunately, this is not a very good estimator because there might be objects in place of that element, namely auxiliary materials like scaffolding or bulk materials, and also the progression states might give false positives. This is very nicely illustrated by this example where we have actually 3 walls, 1 under construction and 2 not being constructed. This not constructed is already a bit nuanced because the anchoring coming out of the floor is already present, but let's say for the sake of brevity that they are not constructed. No rebar fletching has been commenced, so no workers are being paid right now to construct this specific wall. Now, in a classical state-of-the-art method, the wall in the back will be considered fully built because there's a lot of points present on that wall. But the formwork has not been placed and the concrete for this in situ placed wall has not yet been poured. So unfortunately, this wall is not fully constructed. Here in the second stage, in the second epoch, we see the different states advancing from not being constructed to what we feel should be under construction. Namely, the wall on the right has progressed to an under construction state with formwork. The wall in the middle is fully constructed now, but as you can see, there might be clutter in the way, avoiding a proper detection. And in the back, you see that a portion of the wall is constructed, but half of it still needs to be poured, so that would also be under construction. So a binary search here is a little bit short term thinking. We need a more elaborate system, and we need typically some deep learning methods to make a more nuanced choice of what the state of the actual object is. Now, the next task are actually quality control, or the estimation of the tolerances on site. Now, very importantly, this can be both metric and non-metric. For instance, a good example is that a number of construction elements, for instance, this wall, this elevator shaft here, contained by 4 walls on different stories, was actually demolished based on crocodile cracking in the wall surface. This was very hard to detect from a metric stance, but could be very easily identified in the images. So this was not an improper placement, but rather a visual defect of the element. Now, if we talk about tolerance control, we have to talk about coverage, because often we won't see 100% of the element. In fact, due to the occlusions of the connections between different elements, seeing how 100% of an element is virtually impossible. Now, how much do we see of an element? Well, of a floor slab, that might only be close to 40 or 30%. Because some of the top is occluded by elements standing on it, and the bottom side of the slab might not be visible at all. So based on this 30%, we still have to estimate whether that floor is constructed up to its standard or not. And so this coverage should be a metric that should be reported on top of the tolerance control. Now, what we propose is not simply stating whether an object is within or out of tolerance, but actually trying to report the best fit transformation from an object to its observed location, which we found is much more resilient against occlusions of that element. In fact, the parameters that we're trying to fit here are actually the translation in X, Y, and Z direction, but also the rotation around Z, Y, and X. One final aspect is, of course, the absolute versus the relative or internal errors. Those are 3 different errors, but in an observation, we will observe all 3 at the same time. To give you an idea, an absolute error is, of course, your positioning error compared to the GNSS measurement. That might be an absolute error in latitude and longitude of your full construction being shifted to the left or the right. In a classical tolerance control, if you perform an absolute distance measurement, that would immediately put your entire building out of tolerance. But of course, in reality, this is not the case. So we need to separate the absolute errors from the relative ones, namely the distance of a hallway, the width of a door is a relative error. This is close to the internal errors, which might identify differences within the object itself. The opening of a door is a poor example of a relative error because that's within one object. A relative error more is like between two objects or the size of a room or something. But the internal errors might be a piece of piping where one of the pipes is sticking out in an erroneous slope and thus will give a deviating distance calculation. The fifth task that needs to be performed on construction sites has to do with detection, more specifically with semantic segmentation. That is the labeling of every point and or pixel captured on the construction site and assigning it to a certain class and or instance. If we talk about class assignment, we talk about semantic segmentation. If we talk about object assignment, namely the object ID, we talk about instance segmentation. Now, current benchmarks, which benchmark data, acquire around 70 or 80% after a while when enough researchers have proposed methods to solve this labeling task. However, we see a large drop-off when we translate those methods to real-world data. Even more, when we try to use a method from another benchmark on this data that we have right here, we see that there are a lot of incompatibilities due to the domain transfer between, let's say, scans of interior of buildings compared to construction sites. They are very different scenes, and we have noticed that detection methods that work very well indoors don't work well with construction sites that have both indoor and outdoor spaces, and the same can be said for outdoor methods that again don't translate due to the differences between indoor and outdoor data sets. Also, the construction operations themselves are quite unique, and methods tend to not handle those situations very well. Now, to give you an idea what a professional system would look like, well, typically we want to achieve above 90 or 95% detection rate before we can assess that a system is sufficiently reliable, but we are very far from this detection threshold. So the challenge that we will put online will focus on the class and instance labeling of more than 2 billion points and 37,000 images. Now, we have not labeled all of these specifically pixels manually. In fact, we devised an automatic pipeline where we identified the BIM and took the BIM labeling to actually label a lot of the point clouds, which were then manually revised, and then we reprojected those labeled points onto the structure from motion aligned imagery. You can see a depiction right here on the bottom right what such a reprojection would look like. Now, very specifically, you see a lot of holes in that image that still need to be patched, so you cannot have any empty or unlabeled pixels. But that is, of course, because some of this depth estimation of the structure from motion is very sparse, and thus some pixels, whether they are occluded or unreconstructed, will not have any label because there aren't any in the point cloud data. Here we see an overview of one of the point clouds that is being labeled. So here you see a depiction of the BIM in green in Cloud Compare, where we see a classification of all of the columns. Now, it is important to notice that a lot of the classes that are detected on construction sites are in fact not part of the construction themselves. In fact, if we focus only on the structural elements, the primary and then followed by the secondary elements, this will constitute only about 10 or 15 classes, which is very reasonable for a detection task. However, we have a lot of classes, such you saw in the Excel list just below, that have to do with material detection or safety equipment or tracking of vehicles on the site, which is very relevant for construction management, but have little to do with the final building itself. Unfortunately, if we take a look at a data set, actually the majority of points and pixels do not belong to the actual building, but to avoid any false positives, it is important that the detection mechanism actually knows how to deal with those instances and maybe even detect them so they can be used for construction management. Here we see a depiction of what a label production would look like of one of the epochs of the KU Leuven construction site. In fact, we provide multiple labels for construction management and researchers to develop systems on. Namely, we first of all have the segmentation labels, which are the class labels, for instance, wall, ceiling, floor, followed by a material and status label, namely whether they are concrete or steel or cement, followed by a progression label, whether they are constructed or unconstructed, and followed by their object label, which is tied to the IFC GUID, which is a unique identifier for every one of the objects present in the IFC model and the Revit models. So we have aligned very nicely the BIM models with all of the semantics, with the point cloud data, and then also with the image pixels. That brings us to the final task, namely the object detection. This is purely based on the initial segmentation labels and constitutes the retrieval of bounding boxes of certain objects. This task, you might argue whether it is necessary or not, because you already have a segmentation task, but we argue that it is very important to make the distinction between the two. When we talk about the segmentation, this is a fine retrieval of observations that you can use for tolerance control, where it really matters whether a pixel belongs or doesn't belong to a certain object. However, a lot of objects do not need this very high quality segmentation. In fact, most objects on site, like an excavator, need to be tracked very roughly. Once we know its pose more or less, that already gives sufficient information to the construction management to do something with that. So the last task that we need to perform is actually an object detection task in the points and the pixels to retrieve certain objects. Now, as you can see, there's many different bounding boxes to be found in every image. These can, of course, be automatically generated from the segmentation and are again also tied to all of the IFC GUIDs. And to make it very clear, we have produced this Conform de Coco label. Now to conclude, we also have written an API called Geomappy, which is a toolbox that processes both BIM data, structure from motion data, so imagery, geolocated imagery, and point cloud data, even mesh data, and treats it as homogeneous assets. You can query them like there is no difference between all of these entities, and so it is very intuitive to work jointly with BIM data, mesh data, imagery, and point cloud data. Now, the primary task of this toolbox is facilitate the processing, which is currently very unique still for every format, for every data representation, and moreover, we aim to limit the search space which we have to occupy to find a certain element. Because we are tracking a lot of data, we saw the data that was being captured before throughout 17 epochs. We generate so much data that it will become infeasible on construction sites to actually efficiently retrieve observations of a certain object. Imagine that you want to retrieve an object in epoch 14 in a certain story of your building, then you don't want to evaluate every single image and point cloud that was captured on that site. Now, instead, you want a specific date and only the points and pixels in that vicinity, and that requires that we store metadata of every data representation and file format, and we do that in the form of RDF graphs. That is the underlying technology between the internet currently. It is part of the semantic web technologies, and it stores metadata in a very lightweight RDF graph, which consists of a set of nodes, which are tied together with relationships and can be used or can be queried using standardized querying such as SparkQL. Here we see an overview of some of the functionalities in this toolbox, which obviously contain a lot of geometric processing. For instance, the easy retrieval of certain geolocated images or parts of certain meshes in the vicinity of your object. And we have also provided a set of use cases where state-of-the-art methodologies are used to evaluate the progress and the quality of objects on construction sites. You see the link obviously here. I invite you all to go take a look at the website. It is currently being maintained by our PhD researchers, and together with the online benchmark will be published in the future. Actually, the API is open source already, but the benchmark is still under production with the 6 unique tasks. Here you see the landing page for the ITC constructor dataset. Here all the epochs will be made available. Those are being produced as we speak, along with how we produced this information, so it is reproducible, and some of the baseline methods that we propose to generate this information. We will provide detailed information on how to process information to facilitate researchers developing methods, but it can obviously also be used by industry professionals to come and take a look at the data and how maybe they should capture or process their own construction sites. Last of all, here you see the production members or the team members of the ITC Cool Constructor Initiative that looks to advance progress monitoring on construction sites. This is led mainly from the KU Leuven, but of course the members from U20 have done amazing work in both capturing and processing the data. And together we will provide hopefully the first benchmark for construction site data in the world. Thank you very much.
Okay. I'm back. So thank you again now to Martin for this also wonderful presentation, very clear and very hot topics that we present here in our webinar via our both speakers. And that I have to thank you to both again. And there are some questions in the chat that our speakers already start to answer some of them. Maybe I will start with Borja. I don't know if you want to add something to the questions regarding the 12 benefit costs of the assessments. And well, in fact, if you want to add something about the transfer of knowledge of that research to the construction industry, if there are some resistance, what are the questions or what are the reasons to the question that they put and the reasons to have some, if we have some resistance or not to the application on real cases.
Yes, thank you for that. Maybe just addressing I think at least I identified 2 questions from the chat.
Questions, yeah, if you have 2 questions, in fact.
I have one from Fred. I try to respond quickly, but just to keep it as well. But yes and no, right? And this is a tricky question because it depends on who you ask. Of course, the manufacturers claim they are able to achieve this productivity. They have all these wonderful things about the robots, but they are very kind of one-sided view. They are very specific about, the applications where those robots have been tested. And of course, they are trying to sell their product. There have been some academic papers published regarding the independent, if you will, assessment and evaluation of these platforms. Some years ago, actually was in collaboration with the Department of Architecture, I believe, I forgot the name right now. At ETH, we have this in situ fabricator, and we actually analyze in a very systematic and rigorous way the productivity and the value of when these systems might make sense. And we found two things. First, not always it makes sense to robotize projects. It depends on the complexity of the things that you're trying to do. That particular case was building a wall, and the wall was very non-traditional in the sense of the geometry. So it was a trade-off of the complexity of the things that you try to do and the scale of the project, right? One of the challenges we have with construction robots is they are very task-oriented. We don't have the ability to change them quickly from one application to another, except for maybe the cases that I presented where you have a modular approach, where you just add payload for data collection. Those are relatively straightforward and easy. But when you start moving into the actual execution or construction phases, these are a complete different beast, right? So in short, yes, there are some cases in which academicians have been looking into this, but still are very limited. So no one is willing to make these blanket statements of this robot would be much better and will give you this production rate increases and so forth. We are a long way to get to there. But I guess, little by little. Of course, at the end of the day, the questions that you get from contractors is how much money I'm going to save, right? How much is going to improve my, quality? How much is going to, improve my productivity? And we don't have clear, straight answers yet. But when they look at the costs and the infrastructure and the logistics behind bringing robots to their side, they say, not quite ready yet. So this kind of spiral thing that you're not ready to do it, it's not quite there yet. So it's a bit challenging, but I'm optimistic that as they start realizing benefits and they start realizing some of the value that they can get, it would be similar to what happened with BIM, let's say, right? You need to be on board and you need to be ahead to kind of get out of the competition and be productive and be pushing. But also it requires some changes in the way we build. We cannot use the traditional construction sites and start robotizing because they are not meant to do that. So it's many things that have to happen. I don't know if I answered your question, Fred, but I'll be happy to discuss it later. On the second question regarding the VLK versus the navigation and data collection, in this particular application, no, we cannot use the VLK for navigation, mostly because it's not designed to get a quick turnout of the information that is gathered. It's more designed to capture data, high quality data, high fidelity data in a static manner. The other way around would be possible. Depending on the application, you could use the Ooster LiDAR, for example, that I showed, to actually get a reliable, a good enough point cloud that could be used for some things. It could be for maybe preliminary assessment of the quality of some of the elements that are being built. But the other way around is not recommended, because again, the BLK will not give you the requirements for real-time navigation.
Okay, so thank you. Yes, we have one more question from Maddie that if you can please explain the agent localization method that you present.
For the exploration algorithm, you mean, or traditional SLAM?
This is exactly my question. For the agents, did you use traditional SLAM or did you just introduce a new method here?
We are, for the most part, we're using traditional SLAM because it's sufficient for what we want to do. But we want to explore ways in which you can get away with having too much prior information on the site. And for this, we're using exploration algorithms that allow us to define boundaries of areas where the robot can go to, let's say. And it's a combination of 2D SLAM and 3D SLAM, because we want to ensure that we also account for changes in levels when we change, when we consider some of the challenges that we see on site when you have temporary structures, when you have scaffolding and things like that, that would be limiting what you can see with traditional 2D SLAM methods. So yeah, I don't know if that answers your question.
Yeah, thanks.
Thank you.
Thank you. I don't know if Martin is also able to join us in this chat. but I think he also will provide the answers to the questions in the chat, so it's okay for now. I don't know if there are any more questions from the attendees. We have two wonderful presentations, and we are in the schedule, so it's we have more 3 minutes. If you want some more question, please feel free now. Okay, there are some people asking for if the presentation will be shared. Well, usually these webinars are shared in ISPRS, but we will check it later, and we can see in the ISPRS web page. There are a last question. I was wondering about the F1 score threshold. Why above 90%? This is from Karen. I don't know if. Yeah, okay. Martinar is answered, so the question is by in the chat. I think if, of course, I think both speakers are available. If you send an email about if you have any more questions or if you want to ask something more, it's you can send an email because we are reach our time for the webinar. So once again, thank you all for providing this excellent webinar. Both presentations are wonderful. And in both cases, there are a lot of research and a lot of investigation to perform in the next few years. So congratulations for all, and thank you very much, and see you soon, I hope. Bye.
Thank you. Bye.
Thank you. Goodbye.
Bye.